this computer so then we can post it later. Okay, great guys. Good morning to everyone. And today we come back with the first seminar of 2023 session of our group. And we have the pleasure of having Raimon Luna, that is gonna, from the University of Valencia, that is gonna talk to us about the pins. So these neural networks are physics informed to try to extract quasi-normal modes using alternative methods to the usual numerical integration ones. So Raimon, please, you can share your screen and start whenever you're ready.
Thanks, Lorenzo, and thanks everybody for having me. So let me try to share the screen. Yeah, maybe just share everything. Okay. Sorry. How do I start a presentation? Okay, it's not allowing me. Yeah, let me try again.
Could you save this PDF and then just
No, yeah, I don't know, it was working before, but I guess it just is there any
No, right now we can only see
reason why
the folder.
Okay, let me close and open it again. Yeah, I think it got completely stuck. Oh, no, okay. Now, do you see it now? No.
No, because you're not screen sharing now.
Yeah, but I was, so the presentation was in a different window for some reason.
Okay. Okay, now you are starting to screen share, yes.
Now, is it working?
Now it is working perfectly. Okay.
Okay.
Go on,
Okay.
thank you.
Sorry for that. Okay, so in this presentation, as Lorenzo explained, I will try to explain this recent paper that was done in collaboration with Juan Calderón Bustillo and Juan José Oane, Alex Torres, and Tony Font, where we try like a different approach to obtain the quasi-normal modes of the Kerr space-time, the Kerr black hole, by solving the Tucholsky equation. And this new method is essentially using neural networks, or what we call physics-informed neural networks, as a universal approximator for these solutions. Okay, so these methods have been quite popular recently because of the rise of all the machine learning community and the machine learning tools that are really fastly developing right now. So in order to start in the same page, I would like to start with this short review or explanation on what do we mean by artificial neural networks, right? And then we can move on to how we can use these for physics. So, the main idea behind this machine learning, not only neural networks, but pretty much any machine learning model, is like that of a very complicated feat, right? So there's this very famous quote by John von Neumann. With 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And by this, he meant that, you shouldn't use too many parameters to fit a physics model, because, I mean, once you add enough 3 parameters, anything will fit, right? But the idea of machine learning is kind of the opposite. So, okay, we can fit whatever we want. What's wrong with that, right? So let's fit the whole jungle. And for example, here, I'm quoting as an example this very famous GPT-3 model that has 175 billion parameters, right? So the idea here is not to have some physically meaningful model, but to have a model that's as complex as it takes to fit whatever you want, to kind of replicate or interpolate whatever system you have. So with this idea in mind, we can start building some, well, ways to interpolate or approximate multivariate functions. Traditionally, there are many ways to do that, such as these Lagrange interpolating polynomials, which is essentially, well, you have some algorithm to determine the coefficients of a polynomial such that it crosses some particular set of points. From here, you can go to more complex models that match together lower degree polynomials like these splines and the Bezier curves. You can do Taylor series, of course. You can do these Padé approximants, which are a significant improvement over Taylor series for this kind of approximations. A series of orthogonal functions like Fourier series or Chebyshev decomposition or whatever. But the idea of a neural network is kind of an all-purpose approximant for this kind of systems, right? So we start with the most general linear transformation, which is okay. We start with this x naught, and we turn it into some x1, and this is as far as we can get regarding linear transformations, right? So we have a vector, like a collection of x's, like x0, and we can transform it into a x1, but well, with linear coefficients, and this is as far as we can go. But of course, not all transformations or not all functions are linear functions. So the first step that we can take here is to add some nonlinearity to it. So we take whatever was coming from the linear transformation, and we pass it through some function, the sigma, that we call an activation function, that introduces some nonlinear behavior. So usually we think of these values of x as neurons, and then the sigma is something that usually goes from 0 to 1 or to -1 to 1, and is supposed to give an idea of the activation of the neuron, like in some analogy to biological neurons, right? So over the years, many possibilities for the activation function have been used. The first one is the sigmoid kind of function, which is, well, in physics, you may know it as the Fermi-Dirac distribution, that goes from 0 to 1 in a non-linear way. So you can think of it as the function being active when it's close to 1 and being inactive when it goes close to 0. Then there are variations such as this hyperbolic tangent, which does pretty much the same, but from -1 to 1. And then more recently, it's been shown that these very simple functions called the rectified linear units, which is just a linear function that goes from 0 to infinity and then 0 for negative inputs. These ReLU functions are widely used right now in deep learning models, and turn out to be quite useful. And then if you don't want to have a 0 gradient for negative inputs, you have this leaky rectified linear unit, which is pretty much the same, but you have a small slope at the left hand side. Okay. So what you do is, we do what we did at the first step, and then like repeat the same operation many times. So we start with x0. From there, you do the linear transformation. You apply the nonlinear activation function, and you get to x1. Then you repeat the operation to get to x2, and you do this n times up to xn, right? And this right here is what we call a neural network. Okay, in this particular case, it's what we call a fully connected neural network, because we are using all possible linear coefficients between one x and the next one. But that's the main idea. Okay, and what we do here is, well, usually in the literature you will see these equations written in the form of a layer structure, perhaps inspired by some, I don't know, some conveyor belt or some, well, I guess it's inspired by industry. So each one of these x vectors is a layer of neurons, and then these transformations go from one layer to the next one. Okay, and you have some links that look like synapses that are, well, that pretty much correspond to this to the weights. This Wij coefficients that connect each neuron to the ones in the next layer. Okay. So from now on, I will be neglecting this B term, which is called the bias, because all the reasonings are pretty much parallel to that, to the reasonings with W. So just to not repeat myself, I'll be just talking about weights and omitting biases in most of the time. Okay, so now the question is, okay, how do we choose these weights and biases? Because in other interpolants, you had an easy algorithm that told you, okay, how to compute the coefficients of an interpolating polynomial or the weights of Fourier functions or whatever. Here, you don't have an explicit algorithm. So what you have to do is to fit these weights. Okay, so kind of iteratively improve the weights until the network does whatever it's supposed to do. Okay. So what we do is to define this loss function, which is a scalar function, a number, a real number, that is usually chosen to be some metric or some distance, some mathematical distance between what we are getting from the network and what we want to get. Okay, this can be some root mean squared function or some more advanced function depending on the problem. So you can have some likelihood function or whatever. And then what we do is to take gradients of this L, this loss function, with respect to the weights and biases of the network. Okay. So we try to minimize the loss. So we try to find a minimum to get something that gets us something as close as what we want as possible. So what we do is usually some form of gradient descent. So we replace every weight and every bias. Iteratively, we keep subtracting it some fraction of its gradient, right? So we take this W and we replace it by W minus this epsilon times partial L, partial W, right? This epsilon is something that we call the learning rate, and it just allows us to tune how large of a step we want to take every time. If we take a very small learning rate, the training would be very slow. If epsilon is too large, then we would get very large jumps, and we might not converge to a minimum and keep oscillating or whatever. There are more sophisticated algorithms that are pretty much an extension of this gradient descent, but adding some kind of momentum or some inertia to the process that makes the convergence better. One that is very much used is this adaptive momentum algorithm that's called ADAM. And by the way, this is as far as I know, the most cited paper in arXiv on the nodes that introduce this method. And actually, for the training of the neural network in this case, in this presentation, I will be using this ADAM. Okay, so in order to do this gradient descent, we have to compute the gradients. Okay, and this is done by what we call the backpropagation. But as we will now see why it's called backpropagation, but of course it's just the chain rule, right? So if we want to take the derivative of the loss with respect to the last set of omegas, we just apply this chain rule here. If we want to take the gradient with respect to the previous ones, like omega n minus 2, we have to go through the layers, right? So in a reverse order. So we first take the derivative with respect to the xn, then xn with respect to xn minus 1, and then x minus 1 with respect to x minus 2. So in some sense, what we are doing is like going backwards through the path that we took to compute the final output or the loss, okay? And that's why it's called the backpropagation. So usually you have some kind of a graph of all the operations that you are doing in order to compute the loss and then to compute the derivatives. So when you are computing the loss, you are propagating forward in the network, which means to the right in this picture. And then when you are taking derivatives, you are going backwards in the graph. That's why it's called back propagation. So, and finally, of course, if you want to take the derivative with respect to the first weight matrix, you have to go all the way backwards through the network until where you apply these weights. Okay, so you are decreasing this index of the x's, and that's going backwards. So as a summary here, I wanted to provide this dictionary between terms that are widely used in machine learning with the equivalent in general mathematics, right? So when we are talking about a fully connected neural network, we're talking about this, well, applying these linear transformations and then the activation on linear function many times to these x vectors. These x vectors are what we call the neurons, together with the activation functions that we are assigning to them. And we apply this n times, okay? And this is pretty much what we mean by a neural network. When we talk about deep learning, is that because I'm saying here n is larger than 2, because, well, the more layers a network has, the more deep we call it. And so when we have many layers, or well, at least more than one hidden layer, then we call this a deep neural network, okay? Then whenever I say training or learning, I mean just trying to find a minimum, a local minimum of this loss function, okay? And finally, backpropagation is just, well, a fancy name for the chain rule in this kind of operations, okay? Okay, of course, there are more advanced networks. Not all of them are fully connected. Well, the most important ones are networks that are applied whenever we want something to be a shift invariant. So whenever the inputs, the x vector is actually representing some spatial distribution or whatever. So usually it's used in image processing. So this x vector is actually, well, it's actually a two-dimensional, like a matrix. And the values of x are the values of the activation of each pixel in an image. So in this case, we have several problems. First of all, we have many pixels, so it would be very costly to really do a fully connected neural network for these cases. And then we want the result to be shift invariant. So we want the same output, whether you have a cat in one corner of the image or you have the same cat in the other corner. I mean, the output should be pretty much the same. So for these cases, instead of using a general linear transformation, we use a convolution. So instead of multiplying by a matrix, we convolute the input by a matrix or by a set of matrices. And what we are fitting are the entries of these small kernel matrices we're taking the convolutions with. And well, famous models that do this are this LeNet and AlexNet. These are the ones that first showed the real power of these networks. And then when you have some kind of sequential data, so you have data that has a sequence structure, which is mostly used in whatever processing of natural language, like trying to understand speech, understand text, or you have some other time series, like I don't know, the stock values in time or whatever, and you want to predict what will happen in the future. You usually use something that is a recurrent neural network, which takes as input the output of the previous entry. And these kind of things are called there's several models that are used here. This gated recurrent unit or the long short-term memory. And then later on, these attention mechanisms were introduced, and these led up to the transformer models, which are right now the most powerful tools for sequential data, and you have these BERT models and the very famous GPT model. Okay, so now let's go to the part 2, which is well, applying this, how we can apply this to physics, and in particular to the Tucholsky equation. Okay, so the Tucholsky equation is this equation derived in this paper by Saul Tucholsky that uses this Newman-Penrose formalism to separate the perturbations of the Kerr geometry into this big master equation. Okay, so in this case you have this master variable psi, sorry, and you have all kinds of perturbations here. You have several important coefficients. This S coefficient is the spin of the perturbation, which in the gravitational case we'll be taking as -2. And then of course you have well, you have this A, which is the spin parameter of the the rotation parameter of the black hole, which is defined as J over 2m. So it goes from 0 for Schwarzschild black hole to 0.5 or 1/2 for the extremal Kerr. And then, well, you will have some omega, which is the frequency, and you have a separation constant. So this is better shown in this part, where we separate this psi function into the radial and angular parts. So that we have this R part and S part. Okay, and you get two separated differential master equations that now contain explicitly this omega, which is the quasi-normal mode frequency, and this ALM, which is a separation constant that we also have to fit. So we have this system with two eigenvalues. Okay, this was first solved by Lever in this paper, where he used this well, essentially this what is called the continued fraction method, which is a Frobenius method, just expanding these solutions as a Taylor series or as a power series of the variable, and then trying to impose conditions on the coefficients by using the differential equations. So in his case, what he had to impose was regularity, both at the horizon and at infinity, and for that he had to use this quotient rule to ensure that the series was converging, and this was translated into some function that is defined as a continued fraction, and then essentially trying to find the quasi-normal modes was equivalent to finding roots of this continued fraction. So this is why this is called the continued fraction method. Okay, so what he did was to expand this R and S functions as this let's call it the singular part, and then this power series on functions of R and U, which with this U being the cosine of the polar angle. Okay, so what we'll be doing here is doing pretty much the same, but then this regular part that Lever expressed as a power series, we will take it to be well, an arbitrary function, as you will see later on. So let me first explain other methods that have been used to solve the Tucholsky equation and to obtain this mode. Of course, the first one is, well, a little bit of an overkill, but you can directly evolve these equations in time and then extract the frequency of the oscillations. You can use shooting methods. You can use semi-analytic approaches, like converting these master equations into some kind of an effective potential and then solving the bound modes in this potential. You have the WKB approximation. You have this asymptotic iteration methods, and then more sophisticated things are, well, of course, spectral basis decomposition, which is pretty convenient because it reaches really high accuracies. And then more exotic methods are, well, there are many of them. Let me just mention this large T expansion. You can expand this in a very large dimension and then set D to 4, and you can recover part of these modes. Okay, so in this case, what we will do is to do the same thing that Lever did. So take the regular part or the finite part of these R and S functions, and set them to be this thing that I call small f and small g functions, that are functions of this the u variable for the angular part, and then we define this compactified radius, which is called x, which is just the pretty much the inverse of the radius, but normalized by the horizon radius of the black hole. And by doing this, we get two linear second order equations with some coefficients that we have to solve for f and g, as well as for omega and a, which are the two eigenvalues of the system. And following Lever, we will be imposing these normalization conditions that f has to be 1 at the horizon, and then g has to be 1 whenever this u is -1. Okay, so what we do is, okay, what if we just fit these functions, right? Well, we fit these functions together with the eigenvalues, and all of it is equivalent to fitting a bunch of coefficients, right? So the weights and biases of the network, as well as the eigenvalues. So to impose the normalization, we'll be doing this trick, which is called the hard enforcement of boundary conditions, which is just multiplying whatever comes out of the network, which are these n functions, by these factors that go to 0 at the point where we want to impose the boundary condition, and then just adding 1. It is just a dirty trick that accelerates the training process. Okay, so what we did is to devise these two networks, one for f and one for g. And these networks take as input the variables x and u. Then each of them gives a function, and we can plug these functions into the ODEs, into the differential equations, and then get a result, right? And these results, we evaluate this result for a collection of points in x and u, and then we'll take our last function, so the measure of how well or how bad we are doing. We take this function to be an average of the an average of the modulus of the value of these linear operators LF and LG on our set of points. So since the equations contain some derivatives of the functions, we have to obtain first these derivatives. But this, in the case of a network, is done in a pretty straightforward way, because we can still use this backpropagation algorithm to take derivatives of the output of the network with respect to the input. Okay, so, and all of this is automatized in some, in many machine learning environments, but in particular, we'll be using this PyTorch environment. So you only have to define the network as an approximant for the functions f and g, and then it will automatically give you the derivatives on any point without the need of having any grid or finite difference prescription or anything. So since you have to find the network in a say analytic way, it's very easy to obtain derivatives by just keeping track of all the graph operations that you did. Okay. So we adopt these two loss contributions from both networks. We give some special weight to the equation for f, which is a bit more tricky. So this W number is just something that we can tune to get better results. In this case, we will be using 10. So we are giving 10 times more weight to f. Okay, so we did a bit of hyperparameter testing. But what we mean by hyperparameter testing is any parameter that is not being trained. Okay, so anything that's not either a weight, a bias, or anything. So in this case, it's mainly the number of neurons in each layer and the number of hidden layers, or like the number of layers that the network has. As you can see, there's not a very clear trend, but by computing the error that we're committing in the real and imaginary part of the modes after 2000 iterations, we decided to choose 2 layers with 200 neurons each, okay? Like two hidden layers. So you have the input, then 2 hidden layers, and then the output layer, which is just 1 neuron, or 2 neurons actually. Okay, so by doing this, we can start training. Here you have an animation. I hope you can see it in a more or less good quality. So here what you have is how the F and G functions are being trained, are evolving as we do more and more iterations that we call epochs here. So, and here you can see how this omega and A eigenvalues are evolving when we train. The target value, so the value that we take as the correct value, is obtained with this PyCare package, but this is based on some liver-like method. And you can see actually the tables for this in the central website from IST. So as you can see, I start with some pretty random guess, which is omega equals 1 and A equals 4. And then the system kind of converges to the right value. I mean, it doesn't, you can reach up about 3 decimal places to match with the right answer.
So Raimon,
Okay.
can I ask you a question?
Yeah.
Go ahead, Lorenzo. I have a question.
Sorry. No, go Carlos.
Go ahead. Well, my question was, I mean, imagine that you started with something really ridiculous, like A equals 1,000. So would that just mean that it would take longer, or would there be an issue?
I guess it depends on the value. So sometimes it will converge, maybe not. I mean, since if you are very far away, the gradients are very large, so it might not take that long. But it could also happen that you converge to something weird. I mean, to something that's not the solution. It's not guaranteed that you will go into the right minimum.
Right. But
So
it would be clear. There will be some diagnosis that, of course, it wasn't working. The loss function would never converge, I guess.
I guess, yeah. I mean, it's always tricky to train these models. In this case, this model is very simple, so it's kind of easier. But yeah, it's usually not something straightforward to get it to converge.
Okay, thank you.
Okay, can I ask something as well?
Yeah.
The opportunity.
Please.
In the previous slide, I had this idea that you roughly have 1.5% uncertainty on these parameters. But then when we see your example, they really converge to something which is really very close to your target values. It's much smaller than 1%.
So yeah, in this hyperparameter testing, I was using 2000 epochs, and using 5,000. So it's just I am keeping the training for longer.
Okay, because the numbers get really, really very close.
Yeah, well, I mean, it's still not super close. I mean, we have like 3 decimal places or so, but yeah. Yeah, of course, I mean, if you train more, you will tend to get a better result until you saturate the capacity of the network.
Okay, thanks.
Actually, my question is related to this. So you with 5,000 epoch, you arrive to a frequency that is basically 1 in 1,000.
Yeah, kind of, yes.
Kind of, right? So my question would be, compared to other methods, known methods,
Yes.
and considering that you reach 1,000, 1 over 1,000 of error in
Yes.
5,000 epoch, how long is this in real life, 5,000 epoch? Like, is this really a gain with respect to other methods?
Okay, so I mean, this is not in real time, but it's not much faster. I mean, so the whole training might take, I don't know, say 5 minutes, something like that, maybe a bit less, couple minutes. It is still, I would say, quite slower than other methods. So this method is, well, remarkably slow, but it's not terrible. I mean, so you can get one of these modes with, yeah, in a couple of minutes.
And this is with respect to a frequency that you know, a target, you already have a target value. But if you're investigating something that you don't know.
No, so the target value, I mean, yeah, I called it target, but I didn't put this value in the network in any way. This is just, I mean, so the network is reaching this value by itself.
No, yes, okay, I understand. But what I mean is that here you can see that you need 5,000 epoch to reach something that is reliable up to 1,000. But if you would have known, if you would have not known the result,
Okay. So how can you
how many
know
epochs
that you
are confident that you need?
okay, so yeah, that is, well, there are several ways to do this. So, well, first of all, you can look at the loss function, right? So if it's very small, you can be kind of confident that you're not very far from the solution. Another method is how much this result is varying. So you can see that at the end of the training, only like the third and fourth decimal places are changing. So this tells you that you are pretty close. And then, yeah, you can have other methods such as comparing with a known model and seeing, okay, if in this case I needed 5,000 iterations, then maybe in the other cases it will be as well. I don't know. You can decide on several criteria on how to do this.
Okay, thank you, Raimon.
Can I also ask a question?
Yeah, of course.
So my question is, can you be sure that the hyperparameters you choose are well suited for the whole range of parameters of the original problem? I don't know if my question is clear.
Yeah. So what you're asking is actually a common problem in machine learning, which is how do I know that I'm not, so since you are using so many parameters, how do I know that I'm not, say, overfitting? So I'm not using something that works very well in my testing case and very bad in the others.
Yes.
So if you're concerned about that, yeah, I guess you have to do a more extensive kind of testing. Usually what you would do in a more sophisticated case is to have like different sets of data or cases that you want to analyze. You have like the validation set, the cross the development set. So what you would usually do is try to take a significant subset of the cases and test your model there, and then well, try to hope that it will work for the whole case. So based on the cases that you can check, then so try to choose the hyperparameters in this particular subset, and then see how well it does in another subset, and then you can decide, okay, this network works well or not so well.
Raimon, can I ask another question?
Yeah.
So this target value put there is the fundamental state, that is the fundamental mode. Is that it? But you also have the overtones.
Yeah, exactly. So yeah, this I'm going to discuss in a while. Actually, I think it's in next slide. Yeah, here it is.
Can before you go there, can I just ask one thing about the organization of the procedure?
Yes.
So in my mind, I'm not so sure that what I'm going to say is correct, but can I actually have a procedure like this? I don't know the parameter. I have no knowledge of the parameter, but one of the things that I can monitor is the evolution of the fluctuations of omega. And I can actually, in my mind, say that if the fluctuations is in the second decimal case, I have a convergence which is different from the third, from the fourth. And actually these, as the variations get smaller and smaller and smaller, I'm getting to the right number. And actually I could set the precision with which I can actually evaluate this final number. Because if I'm glad that the fluctuations are on the fifth decimal case, I can stop there and I can say, that's the number, and this is the uncertainty on that number. Is this correct?
Yeah, I would say yes, unless something very strange is happening. Usually, yes. When you converge, you start. Well, the variations get smaller and smaller. Of course, you have to be careful because there's also, I mean, the learning rate is not always the same.
Yeah.
And actually, I'm decreasing the learning rate as the training progresses. So you take into account that. I mean, somehow imposing that the training lower as time passes. So, but yeah, if you take into account that you are changing the learning rate and all of this, I think you can say that if the variation is in the 5th decimal place, then you're probably good.
Okay. Thanks. Sorry, Carlos.
Yeah. So regarding overtone, so here's something that we need to compare. We chose this 2.0 mode, 2.0.0 mode, which is the one in Lever's paper, just to compare with the same numbers. It's not for black hole spirals, it's not the most excited, but anyway. So with 2000 iterations, we got something that is say below 1%. It depends on which pin parameter you're using, but it's quite good. And as I said, if you train for longer, you would get something smaller, like below 1 in 1,000 or something. Regarding subdominant mode, and in this case, particularly overtones, so there are several problems. So of course, the easiest mode to reach is the fundamental one, so n equals 0. But if you start with a frequency that is close enough to an overtone frequency, then it will converge to that one instead. Okay, so for example, here we have the 2-2-1 mode, which is the first overtone of the 2-2 mode. We had to start like something at 0.7 or 0.6. But then, so in some sense, if you have some intuition on where the mode should be, then the method gives you all the decimal places. Okay, so it's not completely trivial, but you can get overtones, at least the first few overtones.
But then you would have to start very close to the frequency for those. Is that what you're saying?
Yeah, exactly. So you have to go to the Bayesian of attraction of those modes.
Right.
I haven't, for now, we don't have any method of, say, excluding the first mode and forcing the method to always go to the second. We have to tune it.
Mm-hmm. So if you'd like to get something very fine-tuned, like modes, well, with zero imaginary parts, which you can get in Kerr at the threshold of superradiance, say.
Yeah,
but
well,
this will, of course, be quasi-bound. It's a different problem. So not, you see what I'm saying?
Yeah. So
or it could be for quasi-normal modes, at the threshold between, you know, positive and negative imaginary parts.
Yeah. So I mean, these things you can impose. I mean, so for example, say that you want zero imaginary part. This you can impose and force the imaginary part to be zero.
Mm-hmm.
And then the method will only converge to things that have zero imaginary part.
In a sense, that could be easier even. So because you're putting that very sharp condition from the outset.
Yeah, exactly. So if you have a condition that you can force on the system, then it should work. Or something that you could, well, something that you can do that I've tried a little bit is to say, okay, I want to force the imaginary part to be at least something, right? So to be, if you take into account the negative side, I want the imaginary part to be below some value. Then you don't allow the model to go above that number, and this sometimes works. Okay, so you can kind of push the model towards the solution you want.
Mm-hmm. So it could be a good model to find, say, bound states around Kerr. Yeah.
I think so. Yeah. I mean, it always depends on how the gradient behaves. So if you have I'm thinking now of neutron stars, boson stars and Harry Caron. So sometimes the frequency of the field is like a very sensitive value, right? So if you have very, very sharp well of the loss around the right value. So in these cases, it might be a bit difficult to find the solution by just following the gradient. I don't know if you see what I mean. So the ideal case is to have something that looks like a smooth minimum with wide edges. If you have something that's very spiky, then it's a bit trickier.
Yeah, but again, the fact that, well, some of these modes will only exist for something very particular. Well, of course, that is zero imaginary part, and you don't allow the system to evolve away from this. Then it only focuses on the real part, and then the Bayesian might not be so spiky. That's what I'm trying to say, And,
yeah, this is true. Yeah, I totally agree. Yeah.
Okay, thank you.
Okay, so for the I'm running out of time. So for the final part, I just wanted to discuss some check that we did, which is, well, so first of all, here you have the waveform comparison between the pin modes and this the one that we take as a ground truth is the PyCBC generator, which relies on the lever-like kind of method. So what we did is here we compare for this case, which is 200 solar masses and 0.9 spin parameter. We compare both waveforms and their Fourier transforms, and you can see that they are pretty much indistinguishable to the eye. Okay, so what we wanted to check is, okay, let's say that we wanted to use this as templates for parameter estimation on a real detection, right? So since our accuracy is not perfect, if the detector was good enough, it wouldn't be okay, right? Because we would be comparing with a template that's not perfect. So we wanted to know how good should the detector be in order to distinguish between the right waveform and the pin prediction. Okay, so what we do is to use this, which is Fisher's criterion, which relates the match between two waveforms to the signal to noise ratio that you need to resolve between them. Okay, so if you have a detector that has a signal to noise ratio that's high enough, it will distinguish these two waveforms. We do this match between waveforms in this way, which is pretty much an inner product normalized by this S function, which is the noise distribution of the detector. And for this case, we are using the advanced LIGO distribution. And then what we do is, we normalize this inner product by the norms of the two waveforms separately, and we maximize this over time and phase shifts, and we get some match function f, which can go from 0 to 1 in the case of perfect agreement. And so by using this equation, we could compute for different masses and spins with a given sampling rate of the detector, what signal to noise ratio we need for our estimate to be wrong, right? So if the detector has a lower signal to noise ratio, we can perfectly use our pin modes for parameter estimation. And as you can see, for most of the landscape parameters, this is fine, because we would need some signal to noise ratio above 100, which is pretty high for the current detectors, maybe not so much for the Einstein telescope. The only part that's not so perfect is when you have a very high spin in this 2-2 mode, when you start getting results that are not quite as good, at least for 2000 iterations. You start getting things that are with an SNR below 10, say, okay? But of course, this can be improved with more complex networks and longer trainings and all this kind of stuff. The reason why it depends on the mass is because you have a finite time window for the detection and a finite sampling rate. So it's not just a rescaling of everything. Okay. So in conclusion, I would say that we can use these physics-informed neural networks to solve very generic differential equations, which are both ODEs and PDEs. We've tried both, containing one or more eigenvalues or parameters that have to be fitted. And I want to highlight this very generic part, because pretty much we don't have to impose. So these equations can be whatever we like, pretty much. I mean, we can have them have analytic coefficients, numerical coefficients. The boundary conditions can be pretty much as complex as we want, and the network should be able to solve them, because at the end we're just fitting parameters by gradients set, right? So it's very the scope of applicability of these networks is very wide. Additionally, the implementation of the method is really simple. I mean, this is less than a page of code. As well, if you use one of these machine learning environments that do this back propagation and automatic differentiation by keeping track of all the graph of operations that you used when actually computing the final value. So this is really easy. You can program this in an afternoon. Okay, then the drawbacks are the computation time is larger than with other methods. I mean, usually if you compare this to a spectral method or even to Lever's method, you get the modes in, say, less than a second. In this case, it takes a couple of minutes. But if the network is large enough, you can accelerate and parallelize this in a GPU or in a TPU, this processing units that are routinely used for machine learning, and there are actually even clusters of these. And then the numerical precision is usually lower than other methods, because, well, first of all, these machine learning environments usually use half precision instead of double precision. And then the way that you are fitting these things is not usually super precise, but I would say it's accurate enough for many of the computations. Okay, and that's all for now. Thank you for your attention.
Thank you very much, Raimon, for a very, very interesting seminar. So now we have still 5 minutes for questions. So,
Okay, so
you can raise your hand. I can see George. George, please.
So I thank you, Raimon, for the interesting talk. I have so did you use GPUs to do this work, or do you do it just in CPU?
For all these examples and for the paper, all computations are in a single CPU, not GPU.
Yeah. CPU is very slow to do this type of work. In a GPU, you could do it much faster.
Yeah,
But,
well, so in our case, since the network is very small, I mean, I tried in a GPU that's, I guess, not amazing, and it didn't accelerate a lot. But yeah, I guess we could try.
But did you use mini bashes and something like to parallelize more the training?
So no, I'm using so the amount of points that I'm using is quite low as well. It's like 100 or something. But yeah, this could be further investigated. Yes.
Yeah, because with the GPU and the use of mini bashes, you can parallelize a lot the training, so it can be faster. But yeah, since with the CPU, it's much harder to do that. But yeah, that's what I wanted to ask. So thank you.
Okay, thank you, George. So I see Carlos. Please, Carlos.
Okay, so thank you. It was really a very clear and pedagogical introduction to this. So thank you very much, Raimon. My question is the following. So imagine that for the concrete case that you tackled, which is the Tucholsky question, you wouldn't assume separability. Then could you make some progress in getting the quasi-normal modes using this method?
Yeah, so I've tried solving eigenvalue problems of PDEs. Say if you have like two different variables, in this case would be the angle and the radial coordinate. So you can do it as long as you can impose boundary conditions that are finite and regular. So for example, if you look at what Lever did. So this first part before the power series has something that has some things that behave in a weird way close to the horizon or at infinity. So what the network cannot do is to deal with infinities or anything that's either infinitesimal or infinite. So as long as you can impose boundary conditions that are sensible, then yes.
Did you make a comparison? Say, Kerr Newman is a very difficult case, and so this would be a great test.
Yeah, I could try this. Yeah.
And of course, if that works, there's so many examples that could be tackled that are difficult. So anyway, so that I was wondering, because in this case you could test it, and if you have something that's
yeah, this is nice. Yeah, so since at the end you are using this collection of xi, u, j, it really doesn't matter if each variable goes to a different equation or they both go to the same equation that has two variables, like it's a PDE, right? So yeah, if you can impose the boundary conditions, then it should work fine.
Right, which in principle should be the case, that the boundary conditions are similarly sensible. But yeah, that could be the thing to look into more detail.
Yeah,
but it could be something very, very interesting. Anyway, so that was my question. Thank you.
Yes, and yeah, of course the background solution doesn't have to be analytical. I mean, you could perturb, say, I don't know, a boson star or whatever.
Yeah, exactly. A rotating boson star. Yeah, I mean, we could write down 10 examples that are unsolved in the literature if that works.
Yeah, exactly.
Okay, thank you.
Okay, great. So I see then there is Osvaldo with the hand raised, please.
Yeah, so I wanted to ask, you said it would take about 5 minutes to train on 5,000 epochs for that kind of convergence.
Yes.
So did you, I don't, because you're starting with your functions at step 0 are just constant, right? Or are they random?
So they are random. Yeah. So the weights and biases are initialized in random values. Yes.
Yeah, but okay. So you just have the weights and values.
I mean, you can initialize it. You could initialize the functions to something more.
Right. That's what I was going to say. If you could have some sort of ansatz, just kick the network into gear.
Yeah, well, it's kind of hard to predict the output of the network. So to reverse engineer, if you want a function to get the network to give you this function, I mean, you would have to train it before, which is pretty much what you want to avoid. But what you could do is to define this network as a correction to an ansatz.
Right. That's I don't know, maybe that could cut down on the time it would take.
Yeah.
Train network. Also, you and Carlos had a discussion on the other modes, on how if you train a network with a certain, but you have to start close to the parameter in order to get that excited modes. That did I understand that correctly?
Yeah. So unless you do some trick, yeah, if you wanted to convert to a higher mode, you have to start very close. Otherwise, it will go to the fundamental one.
Okay. I was thinking maybe if you could cut down on the computational time well enough, and if you could parallelize the whole problem well enough, maybe you could do like an immediate search with different starting conditions and
of course, yes.
Yeah.
Another thing that you can do is that once you train the network for one mode, it's kind of easier to train it to another mode. Like say,
Right.
I don't know, you read the spin or because the general shape of the functions is already there.
Exactly. So that, yeah. I mean, it would be interesting to see the results, comparing training from zero and training from a situation like that.
Yeah.
Where-
Yeah, actually, this is what we did in this final part for these plots. This is what we did. So we started at spin 0 and then went up by taking the previous solution as an answer.
And did you notice differences in the convergence time?
So yeah, it tends to converge better. Yeah.
Okay, cool. Thanks. That's all I wanted to ask.
Okay, I see Guillermo with the hand raised, please.
Yeah, thank you. I have a question regarding, so the dimension of the output of the neural network is 2D, right? So you divide the real and the imaginary part, or is it just
Yes,
one
yes,
imaginary number?
Yeah, this is what I do. Usually
So
this
you
package
divide
is-
it, right?
Sorry?
Because if it was just one, if it would be just one imaginary number, then that would bring a lot of questions regarding the activation function.
Yeah, exactly. So this is what I was trying to avoid. So I just did real and imaginary separately. So everything in the network is real.
Okay, and out of curiosity, what's the activation function you're
Here is
using?
hyperbolic tangent.
Okay, because it's faster.
Well, it's a
Or-
smooth function that, yeah.
Okay.
So, yeah. At some point I tried ReLU just for curiosity. It doesn't work that bad, or at least as bad as I would expect, even though it's well, it doesn't have it's not smooth.
Yeah.
But yeah, this is what we usually do.
From my experience, ReLU works well if you want to give it a
Okay.
look, because it's not as stiff as ReLU, and yeah. But also like the output being a vector gives me some questions regarding like the loss function.
Yeah.
You see where I'm going?
The loss. So the thing is that the loss function is a scalar. So I first go.
That's it.
So exactly. So let's see if I have here the picture. So I get these two neurons out of each network. Then I combine them into an imaginary number. Then I plug them into the ODE, and then I take this average of the magnitude. So at the end, the final loss is
the
just
real
a
part.
real
Okay.
scalar number.
Okay. I was okay.
Okay.
Thank you. Also, can you clarify a bit on the hard enforcements, please? Sorry, I don't know if
So yeah, the hard enforcement is that well, there are like two ways to impose boundary conditions or normalization or whatever. So the first one is the soft one, which would be to add terms to this loss function that drag the functions at some particular point to some particular value, right? So you would add here this f at x0 minus 1.
Yeah, sure. It's clear.
So the other way is to multiply the output of the neuron by something that takes it to 0 at the point, and then adding the value. Okay.
Okay.
So a possibility was just to use a linear function here, but we saw in some references that they were using this exponential kind of function, which is, I guess, smoother. So we use this. It works with a linear function as well.
Okay, that's interesting. Okay, so you don't have to minimize the boundary conditions as well. Okay,
exactly. So you are from the beginning, you only allow this system to give you solutions that already satisfy the boundary conditions. So in this case, yeah,
okay.
if
Thank you.
x goes to 1, you get 0 times whatever. Yeah.
Okay. Thank you very much.
Okay, thank you, Guillermo. We have final question. I see Antonio with the raised hand.
Yeah, it's a very quick question, and actually it's a curiosity. I mean, can't you just tell the model that do not go there if I have already found a solution? I mean, it would be interesting to really allow the when you're trying to really find different modes and so on, can you actually tell the mode that, okay, you have already found that one, so don't go there, don't try to find that solution. And I would imagine that actually this I don't know, by changing the loss function or something like this, spoil the loss function whenever you get close to a solution that you have already found. And somehow, because this would mean that the model would be extremely interesting, because you see, it would try to find all the possible solutions for that equation, avoiding the ones that you already found. Is this something that it's possible to do with this?
Yeah, so I would say it's possible. So yeah, as you said, I can spoil the loss function to say forbid going close to something that I already know. But well, you have to do it carefully because you don't want to create fake minima. Okay, so for example, if the model wants to go to a solution and you are adding a repulsion there, it could get in some equilibrium somewhere in between. So you have to be careful. But yeah, I guess you could do it. Yeah, and actually, some people are doing this kind of things for say quantum mechanics problems, that they actually add some minimum energy that they keep rising, so the model doesn't find modes that have an energy lower than that, and so they go jumping on the mode and find them all. So yeah, you can do this kind of things. Yeah.
Okay, sounds interesting, actually. Thank you very much.
Okay, guys, if no one else has more questions, I have a final curiosity before closing. You were showing in the last slide that there was some kind of problem, I mean, issues with high spins. So your SNR was going lower for high spins.
Yeah.
But in the slide before, when you showed the values of no, sorry, 2 slides before, in the table with the, exactly, I can see that the error in the real imaginary part are quite oscillating randomly with spin. So it seems that you can find the spin on the frequency is not really an issue. So no part of the equation that you are solving are dominating the error. But then when you go to the SNR, you start to have a problem for high spins.
So yeah, so well, there are several things to this. So first, this is the 2-0 mode, and where I find the problems is in the 2-2 mode.
Yes.
Secondly, is that in the hyperparameter testing, one of the cases that I was testing was this very close to extremality. So maybe I might be slightly biased in this case. And getting 2 good results for the extremality case. Okay. So in the sense that since I chose the hyperparameters based on how it was performing on the 2-0 mode, then well, I might be getting very good results in the 2-0 mode, but not so good in the 2-2 mode.
But you would say that you expect less precision for higher spin in general.
In general, yes. Actually, it was one of the challenges of the project was to get it to work for high spin, because at first we were getting really bad results after, I don't know, 0.9 or something like that.
Yeah, I was expecting the same. That's why I was looking at the table, but then I was seeing that it was randomly moving this error on the table before. So I was like, okay, that seems that
No,
spin.
for some reason in the 2-0 mode, it works pretty well. It's only in this case, in the 2-2, that we found some, yeah, some problems when you go really, really close.
Okay. Okay. Thank you, Raimon.
Okay.
Guys, I think we are about time. So I would say a big thank to Raimon from everyone, a round of applause for this excellent seminar.
Thanks for having me.
Very good. Thank you so much, Raimon.
Yeah, this was very good, actually. Thank you.
Thanks a lot.
We're gonna wait you in a very soon, and we resume our session next week with a new seminar. Thank you, guys. Have a good day.
Thank you, Lorenzo. Bye bye, everyone. Take
Bye-bye.
care.